All right, we're back on the air. Okay, don't forget that the final exam will be Tuesday the 9th. That's a week from today, 4 to 6:30 p.m. in GCS 118. And it'll be open book, open notes. It'll be based largely on homework assignments, although not 100%, including homework 5, which I'm going to do now, discuss now, but which I didn't assign to be handed in. So I'm assuming that you did it, but you didn't have to hand it in because, first of all, if you did it, it's straightforward and there's nothing tricky about it. So if you did it, you can simply hand it in. I'd grade it and give it back. So why don't we just assume that everybody did it, got it right, but it's fair game for the final exam. So, homework 6, let me just discuss that for a moment. That was a queuing problem. And that was straightforward. It was easy, but some people lost credit on one last part. You were asked to draw the graph of the distribution function of the waiting times. And you were given this formula. And it had two pieces. It was 0 when t is negative, and it was 1 minus rho e to the minus 1 minus rho t over e of x, or t non-negative. You're supposed to draw the graph of that. So here is capital F. Here's t. Here's 0. So when you draw the graph of it, you see that when t is negative, the function is 0. So it should look like that. And then when t is not negative, it's given by this branch. So when you pass through the origin, when t is equal to 0, the exponential is raised to the 0 power, so that's 1. So this value here is 1 minus rho. In our case, rho was 0.8, so this value would be 0.2 right there. And then after that, if that's 1, if you draw this curve, it would look like this. So a typical mistake was for people to draw this curve, but instead of having a discontinuity here, to make it look like this. So if you did that, that was wrong, and I took off usually 2 points for that. So you might do that as sort of tricky, but by this time we've been through this so many times. So if you just draw these curves without thinking about what they mean, well, then it doesn't mean anything. If you think about what it means, you have to say that what this thing says is that the probability that waiting time is less than or equal to some value, some negative value, is not 0, but it's a positive amount, which doesn't make any sense. In fact, I mentioned this in class, but still a lot of people did that. Otherwise, it was straightforward, so everybody just about who did it simply got the answers right. Now, the point of that was to illustrate how probability, the stuff that we've been studying in this course, works in solving problems that are not just examples or toy problems, but are sort of on the boundary between problems that can be solved through simple formulas and problems that are actually difficult and but still meaningful. People actually want to know the answers to, that engineers actually use. So it was designed to be easy to do, but there's a lot to it. And basically there's two pieces to this problem. One is the theory. I tried to explain what the theory meant, but I didn't derive any of it. I just gave you the formulas. And the other is the simulation. The simulation has nothing directly to do with probability. It's simply logic, although in this case there was this sort of tricky idea, which often works in probability, of basing it all on a recurrence, on a recurrence relation, which is sort of a bootstrapping idea. So there's two pieces then. There's the simulation, which is logic, programming, although I did the programming for you, and then there's the theory. And typical in this course is what's been happening is we do some theory in class, and then I give you simulation, I give you some code, and you can either run that code or translate it to something more sophisticated. and then you compare the two, and of course everything always works out. Now, as far as the queuing theory course goes, the course MAP 4260, or MAP 6264. So originally I was teaching only this course. This is a graduate course, and it's called Queuing Theory. But then I decided, because I hadn't taught it in a long time, because you have to have enough students, and we've got all these things competing and not enough faculty and all that, so we haven't been teaching some of these undergraduate electives very often. So this was an undergraduate elective, so I decided to try and merge it and teach the course with one set of lectures, but two separate courses. So I'm not exactly sure how I'm going to handle this, but the idea is that the lectures will be common lectures, and it'll be a feeds course, but in this case, maybe the homeworks will be somewhat different, or maybe the requirements when I grade the homeworks will be somewhat different. That is, there'll be less for the undergraduate version than the graduate version. I'm not exactly sure how it's going to be. But what I want to say, as far as you're concerned, if you're an undergraduate and you're thinking of taking this course, the way you should look at it is this. It's an extension or a continuation of this course. So most people would not take this course. Maybe you could say nobody. Nobody would take this course if they weren't forced to. But I hope at the end of the course that some people actually see that there's something to it. Statistics always has a bad name. I'm not sure why, but this is not statistics anyhow. This is probability primarily. But in any event, at the end, I hope that it sort of catches on with some people, and they think it's interesting and would like to continue. So if you're in that category, then fine. But remember, this is an elective, so there won't be a lot of students taking it, and they'll be primarily good students because they're volunteers. They like it. And so if in taking this course, once you got over the hump of trying to understand what probability is about, what it is, if you like that and you feel that you're fairly good in mathematics, because remember this course is called Queuing Theory, and remember there's two aspects. If you like that kind of stuff, and if you're a reasonably good programmer, because one difference between this course and the Queuing Theory course is that in this course I always give you almost everything that has to be done in terms of the simulation. All you have to do is change one or two instructions just to indicate that you've actually read the code and know what it does, but there's nothing creative in it. But in the Queuing Theory course, what you have is you've got a simulation which is just a logical description of some kind of queuing configuration, just like in Homework 6. And then what I ask you to do is change it somehow, but usually the change requires more insight on your part. So in some sense, it really has little to do with queuing theory, but it does have to do with programming. So if you feel that you could not write these kinds of simulations on your own, not totally on your own, because I give a lot of hints, but I don't give as much as I gave in this course. So if you're okay with, you like that kind of programming, and if you like this kind of mathematics, then I would say take the Queuing Theory course. Let me give an example. In this simulation here, if you understood what was going on, you could see that that there's no maximum number of customers present in the system. In other words, there's no capacity to the queue. So the queue can hold as many customers as the computer can, as high as the computer can count, which for our purposes is infinite. Now, a typical problem in the Queuing Theory course would be take this particular problem and change it so that now there's a finite capacity on the queue, like say 10 or 15 or something of that sort. And what that does is it changes the mathematics because it introduces a boundary condition. So in the course I would then teach that and develop formulas that would allow you to solve the problem and calculate the fraction of messages that are lost because they find the buffer filled to capacity when they arrive. So that's the kind of thing I would do in class, and then the simulation would ask you to add to the current simulation something that has the effect of being able to keep track of how many customers are present so that if a message or customer arrives, when the queue is filled to capacity, that customer is lost. So that's not something that we have in the simulation as it stands. So that's a typical example of the kind of simulations that would occur. In other words, there's a basic structure, and then some piece of it is changed. And what you would have to do is you'd have to write that simulation. So this is a programming problem. It's simple logic, though. It can be done in BASIC, because anything that's not simple enough to be done in BASIC in about 10 instructions is, I can't do it. I restrict myself to BASIC, and BASIC is very good and clear for problems that are small. But if the problems are complicated, then it's no good. That's why you have sophisticated programming languages. So I take that as a constraint. If the logic isn't simple enough so that I can do it in BASIC in about 20 instructions, half of which are overhead, then it's too hard. Nevertheless, that doesn't mean it's easy. Some of these simulations are insightful and tricky. So those are the two aspects. One is, do you like this kind of programming? It's just straightforward logic. And the other is, do you like the kind of mathematics that we've developed in this course? And if the answer is yes, then take this. But if the answer is no, then there's no reason to subject yourself to it, because after all, it's an elective. So you had to take this course, but you don't have to take anything beyond this if you don't like it. Okay, can I answer any questions about that? How many people are considering taking that? So we got about 2. Okay. So hopefully there'll be 10 or so graduate students, and I'm sure there'll be some other people from the other course, so maybe that'll make it work out right. Okay, so that was homework 6. So let me do homework 5. So remember, homework 5 was something that ordinarily I assign, but it's straightforward, but it's something that you should do and think about. But I didn't assign it to be handed in because we didn't have time to grade it and get it back. But I assume that everybody who does it would get full credit on it, because there's really nothing to it. It's just like the queuing problem. It's an illustration, but there's nothing difficult about doing it. So it's based on the central limit theorem, and the idea is to demonstrate that the central limit theorem really does work. And the central limit theorem is obviously very important. You can even tell that from the name. And the central limit theorem says this: if you sample from any population, so there's your urn with your x's in it, and then you calculate the average value. So in other words, you sample n times and you calculate the average, and then you subtract from that the theoretical expected value. Remember, in principle, the average would equal the theoretical expected value if n were infinite. In other words, the average is the sample value, the approximation to the theoretical expected value. Okay, so if I take the difference between the observed average, which is a random variable, and the expected value, which is some constant, and divide that, or calculate it in units of the variance of this population, divided by the sample size, n, the number that I use when I calculate the average, that thing will be normal, 0, 1, the standard normal variable, if n is big enough, no matter what's in this urn. So that's mathematically amazing, and it's also very useful, because it says that I can make a statement about what's in this population, at least in terms of averages, even if I don't know what the distribution is, or what the variabilities are, what the randomness is of the stuff in the urn. So this homework is designed to illustrate that. So here's the homework. So this is homework 5.
What is dx again?
Okay, the x bar,
B of x.
B of x is the variance.
Okay.
And by the way, this can be written several different ways. Often E of x is called mu, and V of x is, the square root of V of x is called the standard deviation. So you see formulas in which instead of having E of x, you have mu, instead of v of x, you could have sigma squared, or if you take the square root, then it's sigma, and you could take the square root of n and you could put it in the numerator. So there are lots of different ways of writing it so that they're equivalent. And finally, remember that x bar of n, by definition, that's 1 over n times x1 plus xn, where x1 is the value of the first sample that you pull out of the urn, x2 is the value of the second, and so forth. So this thing is a sum. This is what's very important here. That's a sum of random variables. Ordinarily, if you wanted to calculate exactly what's going on here, you'd have to take a convolution. But this does all the work for you. But my point is that if I take this x bar of n and put it, instead of writing it this way, write it this way, then I can multiply through by n and I can rearrange it so that I have a statement about a sum of random variables. So the central limit theorem can be viewed as telling you something about the average, or it can be viewed as telling you something about a sum. So I could ask a question that has to do with sums of independent random variables, or about average values, which is just a sum divided by a constant. But in any event, if you recognize that, you can put it in this statement and you can manipulate it to answer the question. So that's valid as long as the n is big enough. And what big enough is, well, that's not clear, but that's going to be illustrated by this homework problem. So for the purposes of illustrating the central limit theorem, I asked this question. Said, what's the probability that the average in a sample of size n lies between two values? And the values I picked were 45 and 55. And in order to make sense of this, you should recognize that for the examples I'm giving, in every case the expected value is 0.5. So we're going to take several different cases. So here is the value of x. And there's going to be three cases. So case 1 is where x is uniform 0, 1. Case 2 is where x is exponential with parameter 2. And case 3 is exactly the one that we did in the previous homeworks, which says that the probability that x is equal to minus 0.2 is 1/2, and the probability that x is equal to 1.2 is 1/2. So each of these has the property that the expected value is 1/2, and so the question is, what's the probability that the average lies within 10% of its theoretical expected value? And in principle, that probability should get larger and larger as n gets bigger and bigger, because because the average will converge to the expected value. But for any finite value of n, the average itself is a random variable, and it could lie outside that range. So the question here is, what's the probability for these three cases that the average will lie within 10% of the theoretical expected value? That's the question. Okay, now notice that from the viewpoint of a homework, when you do the simulation, these things are ones that have been considered before. So there's nothing new here. And it's worth noticing that these three distributions are very different from each other. That is, even though they all have the same expected value, this is a continuous random variable. It's shaped like whose density function is just a square. This is a continuous random variable whose density function has that long tail on it. And this is a discrete random variable. And the central limit theorem doesn't distinguish between them. All it cares about is, in order to use it, I have to know the value of n, and I have to know the expected value of the variance. Okay, so what I want to do is I want to make a statement that is going to relate this probability to the central limit theorem, and then once we do that, we just look it up in the table. Now, there's going to be three cases I want to look at. I want to look at the case where n is equal to 1, the case where n is equal to 25, and the case where n is equal to 100. And then for each case, it's going to be a theory and simulation. Theory, simulation. Theory, simulation. Now, part of the point here is to observe that as n gets bigger, here it's 25, here it's 100, that the probability that x bar will lie within, in this case, 10% of its expected value should get larger. Because in the limit, as n goes to infinity, this probability should be 1. That is, x bar should equal the expected value in principle. So one of the questions is, how large does n have to be before this makes sense? So the theory doesn't tell you that. The theory just assumes that, that we can use the formula and plugs in, and then when you run the simulation, you'll see how close the simulation values are to the theory. And what you'll see is that, in general, when n gets bigger, the theory gets closer and closer to the simulation. Although in any case, it's not necessarily so, because remember, the simulation is random. You can be lucky or unlucky, whereas the theory gives a specific number. Okay, so, and 25 and 100, they're nice values because they have nice even square roots. Square root of 25 is 5, square root of 100 is 10. So I just picked those nice easy numbers. Now, when n is equal to 1, you wouldn't use the central limit theorem. Because first of all, if the central limit theorem works in the limit as n goes to infinity, n equals 1 is as far away from infinity as you can get. And the second thing is that when n is equal to 1, if you know the distribution, then you don't need the central limit theorem, because that's simply picking a single value from an urn and asking for the probability that it lies within that range. Because in the case of n equals 1, x bar, the average of a sample of size 1, is simply that value. Okay, so theory, this is the exact value in theory, has nothing to do with the central limit theorem, but it's in there just to illustrate. In this case, and the other case, where I say theory, I mean central limit theorem. So in some sense, what this does is this helps you understand what level of approximation is in here. Because remember, there are always, in these kinds of problems, there are two kinds of approximation. One is that the simulation is always an approximation, an estimate of the true theoretical result. So there's that error, which is always in there. But in this case, there's an additional error because the central limit theorem, in principle, is accurate only when n goes to infinity. So if these two are different somewhat, then you would expect these two to be a little bit more different. Because in this case, the only error is the error of simulation. But in this case, there's not only the error of simulation, but there's the error of the finiteness of n. Also, it turns out that just like with the homework 6, where everybody makes the mistake of drawing the curve to have positive probabilities for negative values, people make the same kind of mistake here, which is that there's always some people who apply the formula for the central limit theorem when n is equal to 1, which of course doesn't make any sense, but nevertheless they do it, so that's always a couple of points off. But otherwise, aside from making that mistake, there's really no mistake you can make here once I show you what the formula is. Okay, so let me do the exact ones first, because they have nothing to do with the central limit theorem. And you could guess these answers. Okay, suppose that x is uniform 0, 1. What's the probability, and it's an average of 1/2, what's the probability that a sample of size 1 will lie between 0.45 and 0.55? So of course, that simply means this. Here's the density function for the normal, for the uniform variable. Here's the value 1/2. You want to get the probability of lying between 0.45 and 0.55. Well, obviously, that width is 1/10, So that, and so the area of that strip, since the height is 1, is 1/10, so the answer is 1/10. So when you run the simulation, of course, you won't get exactly 1/10, and the difference between these two is the error in the simulation. Okay, case number 2. Now you want to integrate a density function, but now the density function looks like this. Again, you're integrating over the same range, so, but now you need to use calculus. So it's the integral from 0.45 to 0.55 of the density function of an exponential whose parameter is 2. And that, of course, is 2e to the minus 2t dt. So you evaluate the integral if you haven't already done it, and the answer turns out to be 0.0737. So on the final exam, I'd expect you to be able to evaluate integrals like this. I mean, you may not have to do it, but this is straightforward stuff. So if you have a definite integral, you're supposed to have a calculator, and you just press the button and come up with the answer. If you know how to write the integral, but you can't evaluate it, it's really not much use. So I hope you know how to do this. Anyhow, you should check it out, make sure that I got the right answer there. Notice that these answers are quite different. This is 10%, that's 7%. Okay, what about this case here? In this case here, what's the answer? What's the probability that if I sample from an urn one time, in which the probabilities are given by this, that the value that I get will lie between 0.45 and 0.55? Well, half the time it gives me the value minus 0.2. Half the time it gives me the value 1.2. Neither of those lies between 0.45 and 0.55, so the probability is 0. It also turns out that people seem to have more trouble with a simple discrete case than have with a continuous case. Because with a continuous case, you just evaluate an integral, you take an area. With a discrete case, you have to add things up. And I'm not sure why that is, but it always seems that people tend to have trouble with this one, at least up to this point, rather than these two. But these are ones you've all done before, so there's nothing new in this as far as the homework goes. Okay, so now we have to look at the central limit theorem. Now we have to use the central limit theorem for the case n is equal to 25 and n is equal to 100. So now I want to derive the formula for that. So any questions at this point? Okay. So the question that we're asking is, what's the probability that the average value lies between 0.45 and 0.55? So now what I want to do is I want to change this to a statement so I can use the central limit theorem. So I'll rewrite this as the probability that the average minus the expected value divided by the square root of the variance divided by the sample size lies between, and now I do the same thing throughout, so I keep my inequality. So this, instead of, now I would have 0.45 minus e of x. So I subtract e of x, I divide by the square root of the variance divided by n. And same thing on the right-hand side. So we have 0.55 minus e of x divided by the square root of the variance of x divided by n. Okay, so this statement is the same as that statement. And notice, by the way, that when I go from here to here, if I'm going to use this, I have to have the variance. And again, at the beginning of the course, when I explained how you calculate the variance, I kept on saying that the variance will turn out to be useful later on, but you don't know why. But this is an example of it. It turns out that the most important characteristics of a random variable are first its average value, and second of all its variance or its standard deviation. So you see it completely here, and you also see it in the queuing problem, where in the formula for the average waiting time, the variance is explicitly in there. So those are important things to be able to calculate. Okay, so I want to calculate that thing right there. Next step, what I'll do is I will put in the value for the expected value. So this is the same thing now as the probability of 0.45 minus 0.50 divided by the square root of the variance over n. Maybe I'm writing more than is necessary. This thing in the middle I will call z. And here I have 0.55 minus 0.50 divided by the square root of the variance over n equals. Okay, so what I did here was I replaced the e of x by 0.5 because in our problem it's 0.5 in every case. The only thing that differs from one case to the next is the values of n and the variance. And also I use the standard notation of calling this thing z. Okay, now that's the same thing as saying that this is the, what we want to calculate is this, probability. Okay, now what I'm going to do is I'm going to do the arithmetic here. So for example, 0.45 minus 0.50 is minus 0.05. I'm going to take the square root of n and put it up in the numerator, and I'll call the square root of the variance a standard deviation. Okay, so I'm going to write that now like this. This is equal to minus 0.05 square root of n. So I took the square root of n and put it up there. Let's see, as it's written here, I still have it as the square root of the variance. So I'll leave it like that for now. Square root of variance is less than z, is less than plus 0.05 square root of n divided by the square root of the variance. Okay, so all I've done is rewritten this in several simple-minded steps to get it to this statement right here. And now I'm going to apply the central limit theorem. So far, the central limit theorem hasn't come into play, except for the fact that I called this thing z because I know I'm going to want to use it. But now, according to the central limit theorem, this z, if n is large enough, has the standard normal distribution function. So therefore, this would be given by capital phi, that's the distribution function for the standard normal variable, evaluated at this point, minus capital phi evaluated at this point. So that's going to be capital phi, and now I have here 0.05, so I have 0.05 square root of n divided by, and now I'll replace the square root of the variance by the standard deviation. This is just notation. I'll call that sigma. So that's capital phi at this point minus capital phi at this point. So this is capital phi at minus 0.05 square root of n divided by sigma. So this is where the central limit theorem comes in. It says that if z is defined this way, then if n is big enough, it's normally distributed. And if it's normally distributed, then the probability it lies between these 2 points is the distribution function of the standard normal at that point minus the distribution function of the standard normal at this point. So all I have to do is evaluate this thing. One more step here. So I think I'll, let's see. I think I'll go up here. So remember that capital phi of something minus capital phi of minus that thing, well, let me write it down first. This is equal to 2 times capital phi evaluated at 0.05 square root of n over sigma minus 1. Okay, so all I have to do is evaluate this thing for the different values of n and different values of sigma. So any question about that? None of these things have enough ink in them. Okay, so what you should do is you should make sure you can go through these steps and understand, for example, why that is equal to that. And now all I got to do is look this thing up in a table. So what I'm going to do is I'm going to look this up, and I'm going to then calculate it and put it into it. Okay, so in order to do that, let's take this one right here. N is equal to 25, so that means I'm going to put in 5 as the value here. And sigma, well, what's sigma in this case? This is uniform 0, 1, and you calculated in the previous homework that the variance was equal to 1/12. So therefore, sigma would be equal to the square root of 1/12. So now it's algebra to plug into this formula. So I write here square root of 1/12. I write here square root of 25, which is 5. I multiply by that number, and I see what's in there. And the answer turns out to be this. So in this case here, this thing would be 2 times capital Phi. Now, plugging in the appropriate values for n and sigma, and as you check to see whether this is correct, I will get 0.087. There's the -1. Okay, now I look this up in the table, so you should check this out. Go to the table and look up that value, multiply by 2, subtract 1, and it'll turn out to be 0.6156. I don't worry about interpolation or anything like that here. There's no need to be overly accurate, overly precise, because remember, the whole thing's an approximation anyhow. Okay, so in the table, I rounded off to the amount of accuracy that I need to look it up in the table. Then I look that one up, I multiply it by 2, I subtract 1, I get 0.6156. Okay, so that's simple enough. Anybody should be able to do that. All right, now I do it for the second case. What's the variance here? Well, the variance was, what was it, a half? No, it was a quarter. So the standard deviation is the square root of a quarter. So now I plug the square root of a quarter into here. N is still equal to 25. And what I would get is 2 times capital Phi of 0.5. The arithmetic is easy. Minus 1. And that will turn out, if you look it up in the table, to be 0.3830. Okay, how about this one? What was the variance there? That was something you did in homework 3. What was it? 0.49 or something? Right? Anybody remember that? Is that right? Was it 0.49? There's some mumbling there, but I'm not sure. I can't remember these things, right? I didn't do the homework. It's a 0.49? Okay. So that means that sigma is the square root of 0.49, which would be 0.7. I took these things to be easy to calculate. So that means that when I plug those values into the formula, I would get 2 times capital Phi, and inside I get 0.36. Subtract 1, and look that up in the table, that comes out to be 0.2812. So as I say, once I have given you this formula, everybody should be able to plug the numbers in and look things up in the table. So there shouldn't be any problem with that. Okay, now you do the same thing over here, except that over here the only difference between this column and this column is that the square root of n is now 100 instead of 25. So the square root of 25 is 5, the square root of 100 is 10, so that means that since that square root of n is in the numerator, what it does is it doubles the thing that's in parentheses. So that means that this value right here is going to be 2 times capital Phi, evaluated at 1.73, minus 1. That's 2 times this, except that it was rounded. Okay, so it's 2 times 1.73, and that turns out to be equal to 0.9164. The next case, 2 times 0.5 is 1, so that's 2 times capital Phi of 1 minus 1, and that will turn out to be equal to 0.6826. In the third case, 2 times 0.36 turns out to be 0.71. 2 times capital Phi of 0.71 minus 1. Look that up in the table. That's 0.5222. Okay, so those are the theoretical answers, and the simulation answers are just what you get from running the simulation. All the simulation does is simply sample from the urn 1 time, 25 times, 100 times, and calculate the average. And it does each of those 1,000 times. So I have 1,000, in every case, 1,000 values of the x bar, and then it calculates the fraction of x bars that lie in that range. So I gave you the code for that. It's right in front of you. It's no big deal. The only thing would be to generate the values of the random variables, and you've already done that for these 3 cases, so there's nothing new. So you run the simulation, and you get your answers, and of course, then what you want to do is you want to observe how the answers relate to how the theory relates to the simulation. So first of all, what are some observations here? One observation is that as n gets bigger, then it should be true that the probability that I lie closer, that I lie within 10% of my average value, should get larger. Because remember, the theoretical expected value, that's the mathematical model of average. So as n gets bigger, the probability that I lie in that range is going to get bigger. So for n is equal to 1, there's a 10% probability here. Then it goes to about 62%. Then it goes to about 92%. Of course, these things are only approximations. This is exactly true. Nevertheless, when you run the simulation, you'll see that they're reasonably close. That is, whatever value you get here will be reasonably close to that. Whatever value you get here will be reasonably close to that. Okay, so as you go across, as n gets bigger, you are more likely to lie in this range. How about this case? Same thing. 7%, 38%, 68%. How about this case? Never happens. Remember that expected value, that the random variable can have a probability of 0 of actually taking its expected value. That's why expected value is really not a very good name, because if you expect that to happen, you're going to be disappointed. Anyhow, the probability is 0, then 28%, then 52%. And of course, you see, if I did it for a bigger n, then the probability would get higher and higher. Notice also that there's a difference as I go down the column. And what happens is that the bigger the variance is, the more variable the random variable is, the less likely it is to lie within this range. Because the variance is what makes the thing bounce around. So you see that there's a difference here. In this particular case, this is the most variant, has the largest variance. Then this has the next largest variance, and then this has the other way around. This has the smallest variance, the next smallest. This is the smallest. This is larger. That's larger. So as the variance gets larger, the probability that you will bounce farther away from the mean gets larger, and that's indicated here. Same thing over here, 91%, 68%, 52%. Notice also that these numbers are different. 61% is not 38%, is not 28%. And the only difference, as I go down the column, is that they have different values of the variance, because everything else is the same. And also, in each case, the calculation is based solely on the variance. In other words, if I had another population which had the same mean and same variance, even though it had took different values with different probabilities, then the central limit theorem would predict exactly the same results. It's only the mean and the variance that is going to affect the answer in theory, and in practice you'll see that that's true too. That's why the central limit theorem is so useful, so interesting. Okay, so that's it. So it would be reasonable for me to ask a question on the exam that involves the central limit theorem in some form or other. It doesn't have to be exactly this form, but you should be able to manipulate the original statement like this and then look things up in the table. Okay? So I assume everybody could do that, and if you had handed in the homework, you all would have gotten 20 out of 20. Which means, of course, that you all got nothing, right? Because in the sense that your grades are comparable, then if everybody gets the same grade, it doesn't mean anything. I guess. I don't know what it means. Anyhow, I assume everybody would have gotten 20 out of 20 on this, which is almost the case. Most people do get 20 out of 20 on that. So any questions about that? Any question about anything here? How do you use the table? Well, you probably don't remember, but I did that in class. Okay, that's another thing. You should, of course, have a table with you. Remember, it's open book. You can have any book, but you should bring a book with a table. And in Garamani, this table's on page 488, and in Ross, it's on page 570. And the table looks like this. The table gives you values of capital Phi, called phi of x on Ross, page 570. And it has x, and then it has values of x running like this: 0.0, 0.1, 0.2, 0.3, and so on. And it goes all the way down to 3.4. And then it has values running across the top. It says 0.00, 0.01, 0.02, and so forth, and goes to 0.09. And then it has the entries in the table. So, for example, this value here is 0.5000, and this value here is 0.5040, and this value is 0.5398, and so on. So for each value, this represents the value of capital Phi when x is equal to, in this case, 0.00. So, of course, this would be exactly 1/2, because this is the area to the left of the bell-shaped curve to the left of 0. So what this table is tabulating is the area under this bell-shaped curve for the case where sigma is 1 and the mean is 0. So, for example, if I wanted the capital Phi at 0.22, it would be this value right here. That value, whatever's in the table, that would be capital Phi of 0.22. Right? 0.2 plus 0.02. That's the way the table works. So what you should do is you should read this and make sure you understand this. In fact, this is the kind of stuff that if you were a major in some area like some of the social sciences or economics or business or education, something like that, when you take a course in statistics, which you always do because it's very important in applications, this is the kind of thing that you learn like in the first day of class. So everybody knows how to use this table. In fact, one of the problems I always contend is that people use this without understanding where it comes from because they have no mathematical background. That illustrates how important it is. You make people look things up in a table, teach them how to do it, even though they don't have any mathematical background. Because if you required them to have that background, then then they drop out and you wouldn't have anybody doing all this other stuff. But they still need to know it. So the question is whether or not having a table without knowing what the values in the table mean, maybe I'm being too harsh on it, but maybe not, whether that's dangerous information or useful information. My contention is that half the problems in the world are caused by the fact that we're governed by people who look things up in tables that they have no idea where the numbers come from. Right? Look at our economic policy, or taxes or something. Why is that? How can we spend $87 billion that we don't have? Who knows what $87 billion is? Give tax breaks, do all this stuff. Looks like we're going to go broke in no time, and it's all because someone looked up something in some table he had no idea what it was talking about. Maybe not. Maybe they know what they're talking about. I don't know. Okay, so does that answer it? Point is, it's very important. But it's very easy. It's cookbook stuff. Now, not all the tables have exactly the same format, so make sure that you understand whatever table it is that you're using. And you can't borrow tables from somebody else. You don't have to own a book. You can make a Xerox copy of a table before the exam, but once the exam starts, you cannot borrow a table or a book or a calculator from another person. You have to bring in your own. Okay, so I guess we're done with that, right? Okay, so let me go to the next topic, which is what's called confidence intervals. So this is in Ross. Confidence intervals, and it's section 7.3. So it's Ross. This is not in the Garamani book. 7.3, which is on page 223. And the idea is this. We have some population. So there's some population, and the x's are, so we have x1, x2, and so forth. And they're IID. Okay, that means that they are independent, identically distributed. Means that they're selected independently from the same urn, same stuff we always do. And they have an expected value, which we'll call mu. And they have a standard deviation, which we'll call sigma. And then we know, this is the central limit theorem, that x bar minus mu divided by sigma over the square root of n is normal 0, 1. Now, of course, it's only approximately normal 0, 1, depending on n. But what's typically done in applied statistics is people simply assume that. They don't worry about it. All they do is say, okay, we're going to sample from some population, and then we're going to compute this statistic, and that statistic follows a normal distribution, so we can use that table, that one table that everybody uses. So we won't worry about whether or not the central limit theorem applies, whether n is big enough. We'll just do it at this point. Okay, so since this is true, I could do something like this. Here's my normal distribution, my normal density function. And what I'm going to do is I'm going to define a value, which is called z sub alpha over 2. This is standard stuff that I'm talking about now. Standard conventional terminology. And when you do that, that is defined. What that means is that this area to the right of this quantity z is alpha over 2. So z sub alpha over 2 gives me an area to the right of it that's exactly equal to alpha over 2. And by symmetry, z sub minus alpha over 2, or minus z sub alpha over 2, cuts off an area to the left that's equal to alpha over 2. So that means that the area in between is equal to 1 minus alpha. Because remember, the total area has to be 1, so if I cut off alpha over 2 here and alpha over 2 here, I've cut off altogether alpha, so what remains between those is 1 minus alpha. Okay, so from the central limit theorem then, I can make the following statement. I can say that the probability that x bar minus mu divided by sigma over the square root of n lies between minus z sub alpha over 2 and plus z sub alpha over 2. That probability is equal to capital phi of z sub alpha over 2 minus capital phi of minus z sub alpha over 2, which is the same thing, as we know, as 2 times capital phi of z sub alpha over 2 minus 1, and it also must be equal to 1 minus alpha. Okay, so the point is that, assuming the central limit theorem holds, I can define these z values, which are obtained from the table for the normal distribution, and I could say that the probability that this thing lies between those two z values is equal to this, which is the same thing as that. Okay, this may seem abstract at the moment, but when I do an example, you'll see what I mean. Now, this statement can be rewritten. There are lots of ways you can redo these things, so let me redo it and leave it as an exercise for you to show that algebraically what I'm saying is correct. What I'm saying is this. The probability that x bar minus z sub alpha over 2 times sigma over the square root of n is less than mu is less than x bar plus z sub alpha over 2 times sigma over the square root of n. That is equal to 1 minus alpha. This is in the book on page 226. Okay, so first of all, how did I get this? And then second of all, who cares? What does it mean? I got this by starting here, and then I multiplied through by sigma over the square root of n, and then I multiplied through by minus 1, which makes that a minus and that a plus, and changes, makes that a plus, makes that a minus, and changes the direction of the inequality signs. And then I rearrange what I have so that the thing in the middle is mu, and on the left I've got this amount, and the right I've got that amount. Now, this is called a confidence interval for mu. So it looks like a probability statement that says that the probability that mu lies between something and something is given by something. But actually, that's really not the correct interpretation, because the mu is a constant. What this is this is an interval whose endpoints are random variables. So suppose the question is, I have a population, and I would like to know what its mean value is. I would like to know the theoretical expected value. So I could do that by calculating the average, but I don't know how close the average actually lies to the theoretical expected value. All I know is that as the n gets bigger, then I'm likely to lie closer and closer. But I'd like something more precise than that. So what this thing says is that, well, what I can do is I can reach into this urn and I can calculate the average value of the urn. And I calculate the average value and then subtract, which is a random variable. So it's a random value. I subtract from that this amount, and I add to it that amount. Now, the z sub alpha over 2 is something that's obtained from the table, and it's whatever number I need, whatever value from the table, such that it cuts off a value, alpha over 2 to the right and alpha over 2 to the left. So what this statement says then is that if I calculate the endpoints of this interval, x bar minus something and x bar plus something, then that will give me the probability. In fact, that probability will be this, that this random interval contains the value mu. So if my objective is to figure out what the average, what the expected value is of some unknown population, then I can make a statement about that. I can make an experiment which says I'm going to figure out what this mu is by calculating the average, but I'm not just going to use the average by itself. I'm going to use the average minus something and the average plus something, and when I do that, I will know that those limits contain the true expected value with probability 1 minus alpha. So you tell me what alpha you want, and that tells me what the z sub alpha is from the table. I'll illustrate this. And then I can calculate this value and this value. They're constant. The x bar is the random variable, and so I have a probability statement then that allows me to estimate the mean value of a population whose distribution I don't know. However, I do need to know two things. I need to know the sample size. Sometimes the question is, how large a sample size should I pick? Or, but usually I might know that. I mean, that's up to me. But the other thing is I need to know what the standard deviation is. So at first glance, you might say, well, this isn't very useful, because after all, if I don't know the mean, if that's what I'm trying to estimate, how could I expect to already know the standard deviation? So there's two answers to that question. One is, well, we're just starting. And the idea of statistics is, as opposed to probability, is that I've got some population. I don't know what's going on. What I'm going to do is I'm going to perform an experiment, observe the values, and then based on those values, I'm going to go back and I'm going to infer something about the population. So the first thing I do is the simplest thing possible, and this is the simplest thing possible. So one thing you could say is, well, this is the best I can do. It's possible that in any real case, I might actually know what the sigma is, even though I don't know what the mu is. Another possibility is, well, I don't know what it is, but I can estimate it better than I can estimate this. That is, I can get a bound on this. Third possibility is that, well, I can go one more step, which means a little bit more theory, and I can replace the sigma by something else that actually is part of the sample values. And then I've made this more useful because I don't require the knowledge of the sigma. But on the other hand, it makes the theory much more difficult. Okay, so first of all, let me give an argument as to why it might be. Maybe this is artificial, but this is the kind of argument that people give. Because remember, we're just starting at the beginning here. So statistics goes on forever, just like probability does. They branch off at the central limit theorem. So one argument, one example you could give is this. I might have a manufacturing process. And what the manufacturing process does is you set a machine and it chops things off and makes some widget that has an average length to it, let's say. And then what happens is that as time goes on, the machine jiggles around a bit and the average starts to move because the setting in the machine jiggles. So the question is, well, I want to check and see what the true expected value is of the widget that the machine is making. And you'd say, well, let's suppose that I have obtained sigma from past data. It's kind of fuzzy, but let's say I think I know what that was before, and now the machine jiggles. So what happens? That changes the average, but it doesn't change the variability. This is the argument you would make. And you would say, therefore, I'll use the past history here, and I'll make a calculation on this. And if this new calculation then shows that with a high probability I lie within these bounds, then I know that my machine is okay. And if it doesn't, then I reset the machine. So this is a typical use of statistics in manufacturing engineering, quality control. So people in quality control do this kind of thing all the time, and they have charts which work under different assumptions and presumably make everything easier and make it into a cookbook kind of subject. So that's one possibility. Here's another one. I'll look at this next week, or on Thursday, if we have time. You often see in paper about polls. That is, you want to find something like... Is the music going on there? Okay, let's say they have an election. And the question is, what's the probability, what's the likelihood, or what's the percentage vote for one candidate over another? So what you could do is you could simply ask people. You go around and you could pick 1,000 people, and you could say, who are you going to vote for, candidate A or candidate B? And maybe 60% will say they're going to vote for candidate A, and 40% will say they're going to vote for candidate B. So you could say that the probability then, or that the poll shows that the population is 60-40 for candidate A. However, there's an error, could be an error in there, because what you're trying to do is you're trying to infer something about the whole population based on the observation of a subpopulation. So you would like to know how accurate that estimate is. So typically what happens is that you'll see in the newspaper things like the fraction of people who favor candidate A is 60% with 3.5 percentage points of error. So then you say, well, what does 3.5 percentage points of error mean? And the answer is, well, they don't tell you because it's too complicated, but basically it comes out of the central limit theorem. So that's what I want to do next time. So what will happen in that case, what I'm trying to get at is, when I formulate this properly, it'll turn out that the fraction of people who favor a particular candidate is in fact the expected value mu. So what we'll do is we'll figure out how many people we have to question to get a certain accuracy, a certain reliability, and that's measured in terms of percentage of error. So that percentage of error, though, depends on the alpha. So for example, when someone says that candidate A has a 60% of the population with 3.5% points of error, plus or minus 3.5 percentage points, that doesn't mean that you're guaranteed that the true answer lies between 60 plus 3.5% and 60 minus 3.5%. What it means is that there's a certain probability that you lie within those 3.5 percentage points. And what's that probability? That probability is 1 minus alpha. So how do you get that if you don't know what sigma is? And one answer is, well, what you do is you figure out, which I'll show you how to do, you figure out the maximum value sigma could possibly be. And then you plug that into the formula using the argument that if I make sigma as large as it can possibly be, that means I'm being as conservative as I can possibly be. And so the answer that I get will be at least as good as what the theory predicts. Well, it turns out that that's easy to do, and then what I'll do is I'll do that, and then I'll compare it with some stuff I took out of the newspaper from the Miami Herald, which simply tells how many people were questioned, what the percentage point is, and so forth, and we'll see that that corresponds to a confidence interval at the 95% level. And 95%, we'll see, is often the value that's picked. And the reason that they pick 95% is one of these things that, well, if you look things up in the table, then alpha over 2 is 2.5%, and what that means is that the value that appears in the table appears exactly. There's no rounding required, so that makes it simple. And for some reason, 95% sounds like a good number. It could very well be 96%, 94%. So what I want to discuss then is how you actually do this. Once you see it, it's easy. And then you'll realize when you see all of these things in the newspaper about polls, you'll understand what they mean when they say that there's a 95% level of accuracy, or what they mean when they say that how you can judge whether the number of people questioned is sufficient. One of the arguments that people make why they don't like statistics is you'll see that they'll question 800 adults or 1,000 people, and they'll say that with accuracy of with a level of accuracy of 95%, usually they won't even say this, the results are accurate to 3.5 percentage points, to 4 percentage points, or something like that. And then what they'll do is they'll question some people in New Hampshire, and they'll tell you who won the presidential election, even though millions of people haven't voted yet. And it turns out, of course, that they're right, because you only need to question 1,000 people, and the rest of them, if it's a good sample, then in a sense, it's already a foregone conclusion. So, of course, everybody gets pissed off, and they don't want you to publish these results, because if you tell people, when people vote in New Hampshire, what the results are, nobody else will vote, and then the president will be elected by 1,000 voters in New Hampshire. But from a statistical point of view, it's good enough. It's accurate. If you do this right, you can predict, based on a relatively small sample size, what the characteristics are of the whole population, and that's what statistics is about. Okay, so I'll do that next time. I guess that'll be it. So next time I'll do that, plus answer any questions you have for the final exam. Okay, I got homeworks to hand back for some.
Yeah, I left it in your mailbox. Wait.
Okay, Lena. For this, you can